Before we get started with the next talk, we just have a quick announcement that tomorrow after the first break at 11 a.m. At the first break, tomorrow at 11 a.m. Tomorrow at 11 a.m. we're going to take a picture. So just stick around before you go get tea or coffee. Okay, so now on to the next talk. We have Vishnu Nandakumaran to tell us about uniqueness to the Plateau problem near quadratic cones.
Yeah, thank you. So yeah, good to be following Felix. So I can take liberty that you guys are thinking along the same lines. So we will be using a lot of ideas from. Am I too loud? Okay, okay. We'll be using a lot of ideas from the previous talk, but kind of trying to see a much more simpler setting, but kind of trying to question some of the questions you guys had, like what more can you say about, say, these minimal surfaces that are close to these cones. So just to quickly give an overview. So yeah, bad idea to put what are minimal surfaces in a conference on minimal surfaces, but I thought I shouldn't leave anything. So as we saw, the Plateau problem in general, you start with, say, a codimension 2 curve or codimension 2 surface. And the question is if you can find a codimension 1 hypersurface with that as the boundary, right? So the simplest example, like I had a PhD colleague who used to actually come with like these steel wires and dip them in soap. So if you take these two steel wires and dip them in a soap solution, you would essentially have something that's known as a catenoid. And just wanted to have one example, say with much higher genius, just to show the rich structure of minimal surfaces in general. So in general, minimal surfaces are not exactly area minimizing as we saw, but they are just the critical points of the functional. So it's a one-way relation in some sense. But the aim is going to be to study more. It's always harder to study area minimizing functions because you not only have to satisfy the differential equation, but you kind of have to satisfy it globally in some sense, right? And so going back, one of the easiest ways to study this rich structure is to start looking at these tangent cones, right? Because the problem we have is, in general, within the realm of smooth manifolds, you don't have a solution to every Plateau problem. So you have to go into a weaker setup or a weaker notion. But now the problem is, once you're in a weaker notion, just like how you go from functions to distributions, you want to study regularity. So you want to make your solutions as nice as possible, right? And that's kind of the role that what generic regularity also was trying to answer, like the previous hour. But what I'm trying to do here is trying to go a step ahead and try to see, given a cone, can we say more about these surfaces that are close to it? So just going back to the definition. So given any of these manifolds, you can rescale them, and using the monotonicity formula and the stuff, you can actually show that it converges to this self-similar object known as a tangent cone. And the key idea is that the existence of tangent cones, like whether you have a singularity or whether there are possible even flat tangent cones, it kind of goes back to the question of regularity. So for example, between the dimensions of 2 and 6, so that's, so when I'm looking in R7, until R7, I would have no possible area minimizing tangent cones. So the only possible ones are the flat cones. And this kind of relates back to the regularity idea that any minimal surface must be smooth, because as we saw, singular points must go to singular points, right? So now, okay, I lost the flair in saying that, okay, this is sharp because we have the example of the Simon's cone, right? And the Simon's cone kind of was the first example where you had an area minimizing cone which had a singular point. So going back to the definition, it's just like the idea that it's a cone on S3 cross S3. So by this, I just mean that look at S3 cross S3 and then puncture every point to the origin. And okay, And a quick point to note is that this just divides it into two regions, but I like to depict it like this because like when we say a cone, it should look like a ice cream cone that we hold, right? So I like to put in that diagram. But in general, the idea is that somehow as your dimension increased, instead of covering this S3 cross S3 along the boundary, it kind of was more cheaper to cross it across the origin. And that limiting point occurred exactly at, say, the dimension 7. So that's kind of the idea that I try to hold on to. And you can kind of generalize this idea to when instead of having it on S3 cross S3, you can have it on SP cross SQ. And in general, all of these are minimal irrespective of the dimension. But as we saw, grade for 7 uses the 1-phi case isn't minimizing because it's only minimizing from one side. So I guess I can tell more now. It's you kind of have these smoothenings only on one side. You don't have them on one of the side. And basically, apart from that, every case for n greater than 7, right? So these kind of form the model examples for the simplest form of tangent cones you can expect. Well, you can have much more general setup where I didn't start from S3 cross S3, but any area minimizing hypersurface in Sn would give me a similar area minimizing cone. So essentially, you can create that kind of a correspondence. And so any questions still here? I know it was a little bit of a recall, but still good to stop. Okay. So natural question you would ask is, so if I start with, say, such a cone, so I've tried to put in a diagram here. So if I have such a cone and the sigma here, so a couple of my notations are going to be different from today's talk, but like I'll try to make sure I go over them. So if I start with a cone and I have this boundary, which is my S3 cross S3, and then the question is, what if I look at something very close to it? Can I know the solution to the Plato's problem? Because it could be as bad as it looks because we have no control on what it looks like, right? So it kind of goes back to the question from Rukmini, where she was asking, okay, even in the generic regularity condition, okay, even in the generic regularity setup, do we know anything about these smoothenings that we created, right? And so at least for the Plateau problem in a ball, so suppose I look at like within a ball, so it wouldn't be exactly S3 cross S3, but some rescaling of it because S3 cross S3 isn't in the ball. But so if I look at this link, which is like my cone intersected with the boundary of the ball, and then the question is, I perturb it. So now I'm kind of giving an explicit structure to what I mean by perturbing. I look at a graph G that's kind of smooth enough or nice enough on this. And then the question is, if I look along the graph in the normal bundle, so that's what I meant by the green diagram here, can I say what this surface would look like with that G, that new, like, let's call it sigma dash, which is the graph of G at like with that boundary. So I made a small perturbation, and the question is, can I explicitly say something about this? Okay. So, well, your first thought would be, especially like thinking of it relating minimal surfaces to differential equations, the first thought would be, can I just solve kind of the minimal surface equation on the cone with this as the boundary problem? So it just goes back to a Dirichlet kind of problem where I have a PD on a region and I have some value on the boundary, and can I solve for it inward, right? Well, that would mean that can I find such a U with this G as the boundary value? And well, that's definitely not true because we now know that you have these smoothenings that are arbitrarily close enough, but kind of still, can we do better? Can we say something in terms of those smoothenings? So that's kind of the question. Any questions on the question? Okay, seems good. So just a little bit background to quickly go over. So given this cone, and given a function on the cone, I can I'll denote MCU to be the mean curvature operator for that function. So what do I mean by this? Given a function u, and if u is nice enough, so I have to be careful, like, because as I get closer and closer to the singularity, it need not give a realistic function per se. So I would have to work in something known as weighted spaces where it's kind of decaying to the origin. But suppose I put up a very good setup. So given a u in some nice enough space, you can write down this equation and it will be a quasi-linear equation, so non-linear. But the idea here is to kind of study the linear version of this operator and try to predict the structure of the geometry near these quadratic cones. So in general, the biggest advantage is when you study the nonlinear operator for the cone, you only have this second fundamental form, and which is nice enough. So instead of working with S3 cross S3, if I had worked with some other surface, the main problem is I wouldn't have control, or I wouldn't know well enough how this linear operator looks like to study its structure in general. Okay, so going ahead, you can actually kind of decompose this linear operator in terms of like the eigenvalues on the boundary. So I'll just write a couple of more lines than that. So if I have the linear operator for this particular thing, which looks like the Laplacian plus some kind of function that decays at rate 2. The key idea is that you can write this in polar coordinates, and you would just have like the linear operator on the link, essentially. So the idea is that this linear operator would essentially be the Laplacian plus some constant. And this constant is kind of going to play a role because the Laplacian on the sphere is something that we know. We already saw talks and even a poster studying the eigenvalue decomposition of the sphere. So that's well understood. So once you have that decomposition, you can exactly study how these functions look like, but near the cone. Okay. If all this is a little confusing, don't worry. What we essentially do is we know this function, like we know this setup well enough that we can exactly write u. But the problem is that if you look at the lowest modes of u, your gamma 1, so I have this power occurring, so which is my gamma 1 plus and gamma 2 plus and a gamma 3 plus. As I said before, I would want my function u to decay at the origin, only then it makes sense as a physical minimal surface. But these would be much less than 1. So in fact, for the Simon's cone, the easiest case, this would be -2, this would be 1, and so sorry, this would be 0, and this would be 1. So at a linear level, you're kind of able to solve the problem, but that doesn't necessarily translate to a minimal surface. So the question is, how do you realize these modes as like, are these even integrable Jacobi fields? And that's where this whole idea of the Hart-Simon rigidity comes in. So before we go to the Hart-Simon part, I would like to go over another idea where Caffarelli-Hart-Simon kind of worked on this same idea of using the linear and the nonlinear equation, and they were able to solve this for a large enough class of boundary values, but they had to essentially project outside some bad set. So let's forget the nonlinear aspect. Even if we think of it as the linear equation, I would be able to solve this everywhere, but I would have to project outside these bad enough modes. Only then my function u would decay as I go to the origin, right? So essentially, they could do it, but they had to like project the set of boundary values outside some set. Okay, does this make sense? Any questions? So they were partially able to answer our question that we started with, but they still had to forego some boundary values. And yeah.
I'm sorry, I didn't understand this. Can you explain one more time quickly? Sorry.
Yeah, no worries. So essentially, if you think of G as a function on the link, you cannot do this exactly for every G, but I have to project my G outside some function. So you can think of this as being some function on P2. So essentially, they couldn't do it for every boundary value, but they had to project outside some of the bad modes of the eigenfunction. Does that make sense?
Okay, thank you.
And once you have the linear thing, they kind of could solve the nonlinear aspect because you kind of have control in how the nonlinearity behaves, essentially. Yeah. Yeah, so the problem is you kind of have to perturb on both sides. So you essentially don't exactly know it. You would know it modulo this operation. So essentially, you write down your G as some, when you decompose it in its eigenspace, you would write it as some, say, AI times Pi omega, right? So where these are like your eigenvectors for the space of functions. You kind of have to forego the first three. So if I start from I being 1 to infinity, your pi of G would just look like I starting at 4 and then going to infinity. Right? Because you don't want any of these to come. And same way, all of, like, if you go back, all of the gamma I negatives are kind of even more negative than this. So you would have none of them, at least at a linear level. But when you go from the linear to nonlinearity, you exactly don't have control over the pi aspect on the U side. And so that's why you kind of, so essentially saying that modulo this in that equivalence class, you can find one such solution where it forms a singularity. Okay. So now going back to these Hardt-Simon foliations that we saw last. So this definitely is one example where you can't do it, right? Because you have this kind of symmetric object, which is my S plus, which was the Hardt-Simon foliation. And if you think about it, so for the cone, I have such a smoothening. And since it's symmetric with respect to O4 cross O4, or OP plus whatever, P plus 1, OQ plus 1, this essentially corresponds to having a constant function. So if I think of my G as being constant, I wouldn't have any surface because the corresponding minimal surface kind of is the Hardt-Simon foliation, right? But the key idea is that the Hardt-Simon foliation somehow forms the unique thing that you can do. It's the only, it's unique in the sense that it's the only smooth area minimizing hypersurface that's completely contained in that one region, right? So that kind of motivates us to believe that maybe this is the only obstruction to actually solving a Dirichlet kind of problem. And kind of characterizing how these surfaces near these cones look like. So what do I mean by this? So that kind of just encapsulates what I was explaining, that the pi geometrically just removes these three modes. And if you think of it like decaying like r bar 0 kind of corresponds to moving my cone, because that's where I'm remaining constant. So that corresponds to, say, translations. And this corresponds to rotating, because if I have a uniform decay, it could rotate. And in secret, if you look at the Hardt-Simon foliation, it would be graphical, like outside in a far enough, outside of large enough ball, and that decay would exactly be a r power minus 2 decay, of course, with lower order terms. But so it kind of motivates that this corresponds to the Hardt-Simon foliation. And because you have the uniqueness in the Hardt-Simon foliations, you would hope that none of the further lower order terms would contribute or would be integral Jacobi fields. What I mean by that, it would correspond to a minimal surface that you can realize. So you can solve the problem at the linear level, but the solutions at the linear level may not correspond to solutions at the nonlinear level. And you're trying to create this link. And so what Caffarelli Hardt-Simon basically did is they had to forego a part of the boundary to do this. So we try to do the same, but we kind of try to impose a geometric condition to do the same. So what do I mean by this? If I start with, so given a cone, I had this small perturbation which corresponded to a G. What we proved is that, okay, you cannot find a minimal surface that's graphical over C, but you would have to perform this operation, and then you would be able to solve it exactly with that boundary condition. So just repeating what I said. So if I have, I'll try to, if I have the cone, and if I have some small enough perturbation, instead of solving it on the cone, I would first rotate and translate my cone. So I would get, okay, and take a foliate of it. So I would get something new. So this is my, it corresponds to my translations, Q S lambda. And on this, I would exactly be able to solve for the Hartz-Simon coefficient. Okay, so the projection part kind of became in the domain itself where I'm solving for it. And this kind of characterizes how these surfaces look near it. So I'm lying by saying this because like the paper by Edelin and Speller actually doesn't exactly say this, but they say something stronger where they start with any minimal surface that's near the cone and they're able to show that it looks like this. But the motivation for saying this is, before I go to the last part of the talk, I just wanted you guys to know how it would look like, what exactly these surfaces look like, because just saying that, okay, for a perturbation, it's unique, doesn't seem interesting enough until you know what it even looks like. And that kind of was the motivation of the first part. I think I'll hurry because how much time do I have? So just a quick overlook over the proof. Essentially, the idea is similar where you want to solve an equation similar to what Caffarelli-Hartz-Simon did for the cone, but instead of doing it for the cone, I would do it on these foliations. So essentially, given a foliation, I would solve such a boundary value problem, but I would again have a missing set. But the idea is that this missing set kind of fits in a jigsaw. So essentially, what do I mean by this? Given any G, you kind of can find a one-to-one correspondence where after I make this like perturbation, the error here would be 0. So essentially, I would quantify the error, and you would get an implicit function theorem kind of result where it would mean that like for some particular G, you'll be able to find a AQ lambda where it's exactly 0. So that error is 0. So for that particular G, I would find a corresponding surface with that as the boundary. Okay, does this make sense? Okay, any questions? So now we'll go back to the first question where we not only are trying to characterize these surfaces, but honestly, this method was an attempt to even prove that it's unique. So if I had a nice enough regularity here, so if I had a nice enough relation between G and this, I would be able to use my implicit function theorem and I would get that these surfaces are in fact unique, meaning there are no other minimal surfaces with that as the boundary. But we exactly did not get such a strong enough regularity, but we were able to kind of show this completely independently. So without using any of this characterization of how surfaces look near these quadratic cones, we began, say, with a quadratic cone, and we were able to show that if you look at this kind of a small enough perturbation, the surface that you get is purely unique. And this doesn't use any of the characterization that we spoke about before, but in combination, what it says is that if I make a small enough perturbation, it kind of holds to that model of the cone. What do I mean by that? It's either going to be graphical over the cone or graphical over this smoothening of the cone itself, right? So I'll take my last 5 minutes to just discuss the rough proof of what we did here, just to show you what kind of techniques come into play. So the key idea is that I would start with, say, suppose I have the cone and I have two different surfaces. The idea is that these surfaces, like if I have two different surfaces, they cannot move far away, because if they start decaying far away, there's this tool developed by Simon where he does it on the cone, but we kind of re-engineered it a little bit, where if you have any such Jacobi field on the cone and it starts decaying at a rate, because of the structure of the differential equation, the Jacobi field must continue to decay at that rate, meaning it cannot get slower. So if I'm, say, decaying at r power minus 2, at a lower scale, I would at least be r power minus 2, right? So what that means is you kind of can use that to say, to do the same thing, but for these minimal surfaces. So if I'm able to write one of my minimal surface as a graph over the other, so you would ask why would that even be possible? But so that's where like ideas from these Allard theorems come. So we were talking, I think even in the previous lecture, where he was able to show that if the density is nice enough, you can write things as graphs over nearby objects. And you kind of use the same tool where you write M2 as graphs over M1 in large enough regions. And based on how you write down these graphs, you would essentially lead to different forms of contradiction. So what do I mean by that? So just to give a quick overview. So if I have two of these, and I would have annular regions where I'm able to write them as graphs, and they decay fast enough, so they're decaying faster than this critical rate. And after rescaling and playing around with it a little bit, you would actually be able to generate Jacobi fields on the cone. So essentially, whenever I have these MIs, they are converging to my cone, but so I can use the same convergence to make my U converge to some function on the cone, right? And using that function in slightly different setting, you would get different contradictions. So every time you'll get some kind of Jacobi fields on the cone or on these S lambdas, which are not possible. So essentially showing that you cannot have such a function which is non-zero, okay? The hope was to give a quick sketch. I know it's a lot to take in, but I hope at least the idea of the proof came through. So essentially, to give a summary, so basically because of stronger regularity ideas, you kind of can write these things as graphical objects. And once you have graphicality, you use tools from PD which are more recognizable, essentially. So once you have graphicality, you can kind of blow up these functions and generate functions on the cone or on these symmetric objects, but which are kind of not possible, right? And that kind of will then go back and prove that, well, this whole setup itself was not possible. And saying that, okay, if I have two minimal surfaces with the same boundary, they must be the same, essentially. I think I'll roughly stop there. The reference to the main part should be up this week. Should have moved the conference by a week, but it's fine. But the initial construction where I talked about how to model them is a much older result from last year. Thank you. Yeah, just adding to like idea from Felix talk that if you look back, they're trying to find something that is smooth. So the idea here is that we are using much more richer structure, either coming from the quadratic cone aspect or being a hypersurface, being isolated singularity. So the assumptions are a lot. So maybe that even gives scope for doing a lot more. Thanks.
Questions?
So what was the step going from the linearization? I didn't follow very much. The idea, basic idea, going from the linearization to solving the full problem?
So it's basically a fixed point theorem kind of argument. So that part is completely the way Caffarelli, Hart, Simon did it. So essentially what they do is they know how the so if I think I'll explain. So essentially, if you look at my nonlinear operator, you can write it as the linear part plus some nonlinear aspect, but you would have some kind of second order bounds on this operator, the way it behaves. And you kind of use that to, along with the solutions that you get from the linear operator, to look at fixed points. So fixed points for what. So suppose I want to solve, say, mu being 0, right? So this kind of corresponds to like, in a very vague sense. So you see being 0. And if I move it around a little bit, it will just correspond to u times like, I'll have to invert this. So I'm just putting in brackets because it need not be invertible, but once you mod some nice enough kernel, but whatever. So, right. So you would have this. So essentially it's kind of looking at fixed
Okay.
points of this operator, and you can show that it's non-empty, and
I see. Okay.
like
Thanks.
if you choose a small enough neighborhood, it kind of contracts. So that's the argument from Caprelli assignment. Like when we did it, we had to like modify it a lot because the problem is that the linear operator here is very well understood because it's just the link. It's just with spheres, so it's much easier to work. But when we do the same thing, say with my S lambdas, I know nothing about this. The only thing, that's where these gluing ideas come in, where I can write S lambda, which is like this smoothening, as actually being the cone plus the smoothening at the tip, essentially, in an approximate sense. And now I have much more control here. So using this, I have much better understanding of what this looks like, because it looks like LC far away, and near the origin, I would have to get some nice enough estimate for it. So that's kind of the core idea of the first problem that I spoke about. But honestly, this was an attempt to prove this, but it didn't work. So we completely pivoted and did it in a completely different way. It was using this three annulus lemma idea, where you kind of can generate these large enough regions where the function decays nicely enough, and use that to create problems on the cone, essentially. Thanks.
Thank you. Very nice.
Okay, let's thank Vishnu again.